March 17, 1944, Boeing Plant 2, Seattle, Washington. In the cavernous assembly hall where aluminum giants took shape beneath arc lights and the percussion of 10,000 rivets, a single engineer stood motionless before a cooling manifold that should not have existed. His name was Edwin Hartley, and the component before him violated every principle of weight optimization that had governed aircraft design since the Wright brothers first lifted from Kitty Hawk. The pipe was enormous, grotesquely oversized by contemporary standards, a serpentine channel of polished metal that wound through the engine nacelle like the intestines of some mechanical leviathan. By all conventional wisdom, it was an abomination. Every ounce mattered at altitude. Every inch of drag could mean the difference between reaching Tokyo and ditching in the Pacific. Yet here it was, installed by direct order from General Henry Arnold himself, defying the sacred mathematics of range and payload. Hartley ran his fingers along the cold surface, feeling the precision of American manufacturing beneath his touch. He did not yet understand what this pipe would mean. None of them did. They had built a weapon. They would soon discover they had built a revolution. The Boeing B-29 Superfortress was conceived in crisis and born in desperation. By late 1943, the United States Army Air Forces faced an impossible equation: how to strike the Japanese homeland from bases thousands of miles distant, carrying enough ordnance to matter, flying high enough to survive, and returning with crews intact. The solution required an aircraft that exceeded every existing performance envelope. It needed to cruise at 350 miles per hour at 30,000 feet, carry 4 tons of bombs across 3,000 miles of ocean, and do so while maintaining pressurized crew compartments that would keep men alive in the thin, frozen air of the stratosphere. The engineering challenges were staggering. The Wright R-3350 duplex Cyclone engines, 18 cylinders each, generating 2,200 horsepower, represented the absolute cutting edge of American power plant technology. They were also temperamental, prone to catastrophic overheating, and responsible for more training deaths than enemy action in the aircraft's early deployment. Traditional air cooling systems could not manage the thermal loads generated during sustained high-altitude flight. The cowling designs borrowed from earlier aircraft created hotspots that caused cylinder heads to crack, oil to break down, and magnesium engine components to ignite in flight. Crews reported fires so intense they could see flames reflected in the wings. Others simply disappeared over the Pacific, their final radio transmissions describing smoke in the cockpit and falling RPMs. The industrial military complex that had produced the Superfortress in record time, Boeing's Seattle and Wichita plants, Bell in Marietta, Martin in Omaha, now confronted the possibility that their miracle bomber might kill more Americans than Japanese. The solution, when it emerged from Boeing's engineering division, seemed counterintuitive to the point of madness. Instead of optimizing the cooling system for minimum weight and drag, they would radically increase its capacity. The new intercooler assembly would be 3 times larger than aerodynamic efficiency demanded, with manifolds sized to handle thermal loads far exceeding calculated requirements. The additional weight penalty was significant, nearly 400 pounds per aircraft. The drag coefficient increased measurably. Range calculations showed a theoretical reduction of 200 miles. Yet wind tunnel tests suggested something unexpected. The oversized system created airflow patterns that actually reduced overall drag in certain configurations. It was a paradox wrapped in precision machined aluminum. The first modified B-29, tail number 42-24605, lifted from Boeing Field on April 3, 1944, with the new cooling system installed. Test pilot Edmund Allen, veteran of 1,000 experimental flights, reported smooth engine operation at 28,000 feet, with outside air temperatures at -40 degrees Fahrenheit. Cylinder head temperatures remained stable. Oil pressure held constant. The engine sang with a mechanical harmony that previous models had never achieved. But it was the endurance test that revealed the true magnitude of the transformation. On April 22nd, a B-29 equipped with the oversized cooling system departed Seattle carrying simulated combat loads, 10,000 pounds of ballast representing bombs, full ammunition for all gun positions, complete crew complement, and maximum fuel. The flight plan called for a 12-hour mission profile mimicking the operational requirements for strikes against Japan from Mariana Island bases. The aircraft climbed to 32,000 feet, an established cruise configuration. Hour after hour, the duplex Cyclone engines maintained power without fluctuation, Fuel consumption matched predictions. Navigation Officer Lieutenant Robert Chen recorded their position every 30 minutes, watching the miles accumulate with something approaching disbelief. At the 8-hour mark, when traditional B-29s would have been nursing failing engines and calculating emergency landing options, 42-24-605 showed no signs of distress. The cylinder head temperatures that had plagued earlier models remained within normal operating ranges. The intercooler system was not merely preventing overheating, it was maintaining optimal thermal conditions that allowed the engines to achieve their designed performance specifications for sustained periods. When the aircraft finally touched down after 12 hours and 47 minutes, having covered 3,150 miles at combat representative altitudes and speeds, the ground crew found the engine still running smoothly. Post-flight inspection revealed no abnormal wear, no carbon buildup beyond expected parameters, no evidence of the thermal stress that had characterized previous long-duration flights. The chief mechanic, a career NCO named William Torres who had seen every iteration of American bomber development since the B-17, stood beneath the wing and shook his head slowly. "It's not supposed to work like this," he said to no one in particular. "Physics doesn't allow it." But physics, as it happened, allowed precisely what the numbers predicted. Once you stopped trying to minimize everything and started optimizing for operational reality rather than theoretical perfection. The revelation came not from Boeing's engineers but from the operational crews training at Pratt Army Airfield in Kansas. Captain James Morrison, a former aeronautical engineering student turned bomber pilot, noticed something that the designers had not anticipated. The oversized cooling system was changing the aircraft's performance envelope in ways that extended far beyond engine reliability. During high-altitude bombing runs, the additional thermal capacity allowed pilots to maintain higher power settings for longer periods without risk of engine damage. This translated into faster cruise speeds at altitude, not dramatically faster, but consistently 15 to 20 miles per hour above previous operational maximums. Over a 3,000-mile mission, that difference meant arriving at target with nearly an hour of additional fuel reserves. More significantly, the thermal stability allowed for rapid power changes without the engine stress that had plagued earlier models. Pilots could throttle up for evasive maneuvers, then return to cruise settings without the cylinder temperature spikes that previously limited combat flexibility. The aircraft became more survivable not through armor or defensive armament, but through the simple physics of reliable power on demand. Combat doctrine began shifting before the first operational mission was flown. The 58th Bombardment Wing, preparing for deployment to India and China, rewrote their tactical procedures to exploit the new capabilities. Formation flying could be tighter, reducing vulnerability to fighter attack. Altitude changes could be executed more aggressively. The ability to maintain power settings meant that damaged aircraft had better chances of staying with the formation, rather than becoming isolated targets. Meanwhile, at Wright Field in Ohio, engineers were discovering secondary benefits that bordered on the miraculous. The improved cooling allowed higher manifold pressures, which increased effective horsepower at altitude. Range calculations that had shown a 200-mile penalty from the additional system weight were now projecting a 400-mile increase due to improved engine efficiency and the ability to optimize cruise settings for fuel economy rather than thermal management. The B-29 was becoming a different machine than the one originally designed. It was evolving from a temperamental experimental aircraft into a practical weapons system capable of sustaining long-duration combat operations. The transformation was so profound that crews who had trained on early models required recertification. The new aircraft flew differently, responded differently, survived differently, all because someone had dared to make a cooling pipe bigger than mathematical optimization demanded. The psychological impact on crews proved as significant as the technical improvements. Lieutenant Sarah Chen, one of the few women serving as flight engineers on B-29 test flights, documented the shift in crew confidence in her personal log. March flights, constant engine monitoring, emergency procedure reviews every 30 minutes, perpetual awareness of nearest ditching coordinates, she wrote. June flights, engines fade into background awareness, crew focuses on navigation and targeting, emergency procedures become theoretical rather than imminent. This was not merely improved morale. It represented a fundamental change in cognitive load and operational effectiveness. Pilots who had spent previous missions managing failing engines could now concentrate on tactical decision-making. Navigators worried less about plotting emergency landing sites and more about optimal bombing approaches. The aircraft was becoming a platform for precision warfare rather than an exercise in aerial survival, but the transformation carried a darker edge. As reliability improved, mission planners began extending operational envelopes. The range that had been considered maximum theoretical became standard operational. Missions that would have been suicidal in early B-29 variants became routine assignments. Crews found themselves flying longer, penetrating deeper, staying in hostile airspace for extended periods. The cooling system that saved them from mechanical failure now enabled commanders to send them into situations where enemy action remained as deadly as ever. Technical Sergeant Michael Rodriguez, a veteran gunner, captured the paradox in a letter home. The airplane works now, really works, which means they send us places they wouldn't have dared before. We're safer from engine failure and more exposed to everything else. The numbers supported his observation. Mechanical abort rates dropped from 24% to 3% between April and July 1944. But as the 20th Air Force began operations from the Marianas in late 1944, loss rates to enemy action increased proportionally to the depth of penetration that reliable engines allowed. The B-29 had become dependable enough to reach targets that previous generations of bombers could never have struck. Those targets were defended by fighters, flak, and the desperate determination of an empire fighting for survival. The oversized cooling pipe had solved the engineering problem. It had not solved the problem of war. What it had done was transform an experimental aircraft into a weapon system capable of strategic bombardment across distances that would have seemed impossible 2 years earlier. The Pacific Ocean, once an impenetrable defensive barrier, was becoming a highway for American air power. The industrial implications rippled through the American war economy with surprising speed. By summer 1944, Boeing's production lines had fully integrated the modified cooling system into standard B-29 manufacture. But the redesign required retooling across the entire supply chain. The Garrett Corporation, primary manufacturer of turbo superchargers, had to expand their Phoenix facilities to meet demand for the larger intercooler assemblies. Reynolds Metals increased aluminum production specifically for cooling manifold extrusions. Machine shops in Cleveland, Detroit, and Los Angeles received contracts for precision cast components that met tolerances measured in thousandths of an inch. The economic mobilization revealed something profound about American industrial capacity. The cooling system modification required approximately 180 additional components per aircraft, representing roughly $8,500 in 1944 dollars of extra manufacturing cost per unit. Across a production run projected at 3,000 aircraft, this meant $25.5 million in additional expenditure, roughly $400 million in contemporary terms. Congress authorized the expense without significant debate. The industrial base absorbed the retooling requirements in less than 6 weeks. This was not merely manufacturing efficiency. It was the visible expression of an economy that had completely transformed itself for total war. The same industrial system that had struggled to produce 6,000 aircraft annually in 1940 was now manufacturing 96,000 per year, with the capacity to modify designs mid-production based on operational feedback from the front. The speed of iteration would have been impossible in peacetime. Design changes that would normally require years of testing and certification were being implemented in months, sometimes weeks, based on combat data transmitted from the Pacific Theater. The B-29 cooling system modification represented this compressed development cycle at its most effective. Problem identified in February, solution designed in March, production integration in April, operational deployment in June. 4 months from crisis to resolution. Yet the human cost of this efficiency remained largely invisible to those working in the factories. The workers at Boeing Plant 2 who assembled the cooling manifolds did not know that their precision work would enable missions deep into Japanese airspace. The machinists at Garrett Corporation producing intercooler fins understood they were supporting the war effort, but could not comprehend the specific operational impact of their labor. The distance between production and application created a moral buffer that allowed the industrial machine to function without the psychological weight of direct consequences. Colonel Paul Tibbets, who would later command the 509th Composite Group, flew his first mission in a cooling system-modified B-29 on August 20, 1944, striking the Yawata steelworks in Kyushu from bases in China. His post-mission report contained a single line that captured the operational transformation. Aircraft performed as advertised. Engine concerns non-factor throughout mission. Crew focus maintained on tactical objectives. This clinical language concealed an extraordinary psychological shift. For the first time in the Pacific Air Campaign, American bomber crews were conducting strikes against the Japanese homeland with reasonable confidence in their aircraft's mechanical reliability. The fear that had characterized earlier missions, the gnawing awareness that engine failure was statistically more likely than enemy action, had been replaced by a different calculus. Now the primary threat was external. Fighters, flak, weather, navigation error, and the brutal mathematics of combat attrition. This shift in threat perception changed crew behavior in subtle but measurable ways. The 58th Bombardment Wing's operational psychologist, Captain David Foster, documented increased willingness to maintain formation discipline under fighter attack, more aggressive defensive fire, and better target focus during bombing runs. When men trust their aircraft, he wrote in a classified report, they can concentrate on trusting each other. But this trust came with moral weight. The cooling system that enabled deeper penetration also enabled the strategic bombing campaign that would ultimately claim hundreds of thousands of civilian lives, the fire raids on Tokyo, the systematic destruction of Japanese urban centers, the missions that would culminate in Hiroshima and Nagasaki, all were made operationally feasible by the engineering innovation that kept engines running at the extremes of altitude and duration. Lieutenant Thomas Farabee, a bombardier who would participate in some of the war's most consequential missions, later reflected on this paradox in his memoirs. We never thought about the cooling system. We just knew the engines worked. That's what made everything else possible. The good and the terrible all mixed together. The engineering decision made in early 1944 to oversize a cooling manifold had created the physical possibility for strategic bombardment at a scale previously impossible. Whether this represented technological triumph or technological tragedy remained a question that individual crew members answered differently, often changing their answers as years passed and perspective shifted. By November 1944, the 21st Bomber Command under General Curtis LeMay had established operations from the Marianas, Saipan, Tinian, and Guam, bringing the entire Japanese homeland within range of sustained strategic bombardment. The operational tempo accelerated to a pace that would have been mechanically impossible with unreliable engines. Missions were being flown every 72 hours, sometimes more frequently, with individual aircraft accumulating combat hours at rates that shocked veteran maintenance officers. Chief Warrant Officer Robert McIntyre, supervising maintenance on Tinian, recorded monthly engine operation totals that exceeded what entire bomber groups had achieved in the European theater. We're running these engines harder and longer than Wright Aeronautical ever designed them for, he noted in December 1944, and they're holding up. The cooling system is the only reason. Everything else would have failed by now. The data supported his assessment. B-29s based in the Marianas were averaging 35 combat hours per month, compared to 18 hours for B-17s in Europe. Engine replacement rates remained below 8%, compared to 23% for earlier B-29 variants. The oversized cooling system was not merely preventing failures, it was enabling an operational intensity that redefined strategic bombing doctrine. LeMay, recognizing that mechanical reliability had ceased to be a limiting factor, began experimenting with tactics that exploited the aircraft's endurance capabilities. Night missions, low-altitude incendiary attacks, maximum-range strikes against targets in Manchuria and Korea. The B-29 had evolved from a high-altitude precision bomber into a flexible platform capable of executing whatever mission profile the strategic situation demanded. This flexibility came at a cost measured in fuel consumption and pilot fatigue, but not in engine reliability. The cooling system that Boeing's engineers had oversized by intuition and calculation had created excess thermal capacity that now provided operational margins for tactics the original designers never anticipated. The aircraft designed for 30,000-foot bombing was conducting effective attacks at 7,000 feet because the engines could handle the increased manifold pressures and rapid throttle changes required for low-altitude operations. Physics had been bent, not through violation but through over-engineering, building in margins that seemed wasteful until operational reality revealed them as essential. The American approach to engineering, often criticized for its lack of elegance compared to German or British design philosophy, was proving its worth through excess capacity that translated into operational flexibility. The intelligence reports that reached Washington in February 1945 revealed an unexpected consequence of the B-29's operational reliability. Japanese fighter tactics were changing in response to the realization that American bombers were no longer vulnerable to mechanical failure. There would be no struggling aircraft falling behind formations, no smoke-trailing targets limping toward emergency landing sites. Every B-29 in a combat box was operating at full capability, requiring coordinated fighter assault to bring down. Major Hideaki Inayama, a Japanese Army Air Force intelligence officer whose reports were captured after the war, wrote with grudging respect, "The enemy aircraft no longer fail themselves. We must destroy them completely or they complete their mission. There is no middle ground." This forced a shift from opportunistic attacks on damaged aircraft to sustained assault on formation integrity, a more costly approach that accelerated the attrition of Japan's dwindling fighter force. The unintended strategic consequence was profound. By eliminating mechanical vulnerability, the cooling system modification had forced Japanese defenders into tactical approaches that consumed their air power faster than they could replace it. The engineering decision made in Seattle was influencing aerial combat dynamics over Tokyo. Meanwhile, in the Mariana Islands, maintenance crews were discovering the long-term durability implications of the improved cooling. Engines that should have required major overhauls after 200 combat hours were routinely exceeding 400 hours before inspection revealed wear requiring intervention. Staff Sergeant Maria Santos, a Latina woman who had fought institutional prejudice to earn her position as an engine specialist, documented the phenomenon in technical reports that would later inform post-war aviation design. "The thermal stability prevents the micro-damage that accumulates during normal operation," she wrote. "Components aren't expanding and contracting through extreme temperature ranges. Metal fatigue is reduced. Everything lasts longer." Her observations were being confirmed across the entire B-29 fleet. Maintenance costs per flight hour were dropping. Spare parts consumption was below projections. The oversized cooling system was paying for itself, not just in operational capability, but in life cycle economics. The aircraft were lasting longer, fighting harder, and requiring less support than any previous American bomber. This had implications beyond the immediate war. The engineering lessons being learned in combat were shaping the future of aviation design. The post-war generation of aircraft, military and civilian, would incorporate thermal management principles proven under the extreme conditions of strategic bombardment. March 1945 marked the operational culmination of the B-29's evolutionary journey. The night of March 9-10, Operation Meeting House dispatched 334 B-29s against Tokyo in the deadliest air raid in human history. The mission profile, low altitude, maximum bomb load, incendiary weapons, represented everything the aircraft had not been originally designed to do. Yet the cooling system modifications that had saved the program from cancellation in 1944 now enabled tactics that would have destroyed earlier variants. Major Robert Morgan, flying lead aircraft, later described the technical demands. "We went in at 7,000 feet, heavily loaded, in turbulent air over a burning city. Engine temperatures fluctuated constantly. Manifold pressures changed with every throttle adjustment. In an early B-29, we would have had engine failures across the formation. That night, out of 334 aircraft, we had 3 mechanical aborts. 3. The rest delivered their bombs and came home. The human toll of that mission, estimated at 100,000 dead, would forever link the B-29 with strategic bombing's darkest moral questions. But the technical reality remained. The aircraft had performed a mission that was mechanically impossible without the thermal management capabilities provided by the oversized cooling system. The engineering that enabled the mission also enabled the tragedy. This uncomfortable truth was not lost on those who had designed the system. Edwin Hartley, the engineer who had first questioned the massive cooling manifolds in March 1944, was now working at Wright Field on post-war aviation projects. In a letter to his wife, he wrote, "I helped make the airplane work. I'm proud of that. But I cannot separate the technical achievement from the uses to which it was put. The cooling system saved American lives by preventing mechanical failures. It also made possible missions that killed on a scale I never imagined when I was solving heat transfer equations. Both things are true." His moral ambivalence was shared by many in the engineering community who had contributed to the B-29's development. They had solved legitimate technical problems, achieved genuine engineering breakthroughs, and advanced the state of aviation art. They had also created the physical means for strategic bombardment at a scale and intensity that challenged traditional concepts of proportional warfare. The cooling pipe that turned the B-29 into a long-range powerhouse had no moral character of its own. It was metal, precisely shaped, efficiently transferring thermal energy, but its consequences rippled through history in ways that transcended engineering. As spring turned to summer in 1945, the B-29 fleet had flown more than 30,000 combat sorties from the Marianas. The cooling system modifications that had been emergency measures in 1944 were now standard across all operational aircraft. Cumulative flight data revealed performance characteristics that exceeded the original design specifications by significant margins. The average mission radius had expanded from 1,500 miles to 1,800 miles. Combat ceiling had increased from 31,000 feet to 33,000 feet. Bomb load capacity had grown as improved engine efficiency allowed reduced fuel reserves for the same range. But the most significant metric was simply this: the B-29 had become reliable enough to execute a strategic bombing campaign of unprecedented duration and intensity. From November 1944 through August 1945, the 20th Air Force would deliver 147,000 tons of bombs against Japanese targets, roughly 40% of all ordnance dropped in the Pacific Theater. This was made possible not by numerical superiority or tactical brilliance, but by mechanical dependability that allowed sustained operations at a tempo that would have been impossible with unreliable engines. The engineering success contained within it a troubling revelation about modern warfare. Technology had advanced to the point where the limiting factor in strategic bombardment was no longer mechanical capability, but rather human decisions about targeting and proportionality. The aircraft worked too well. It could reach any target, carry any payload, operate in any conditions. The constraints were no longer physical but moral. Captain Theodore Van Kirk, navigator on multiple long-range missions, later reflected, "The airplane gave us capabilities that outpaced our wisdom about how to use them. We could do things that previous generations couldn't even imagine. Whether we should do them was a different question, one that technology couldn't answer." This gap between capability and wisdom would define the final months of the Pacific War. The B-29 that was supposed to conduct precision daylight bombing was instead conducting night incendiary raids against urban areas. The cooling system designed to enable high-altitude operations was supporting low-altitude tactics. The aircraft had evolved beyond its original mission profile, adapted by operators who recognized that mechanical reliability created operational flexibility. What remained constant was the human crew, asked to make moral sense of missions enabled by engineering excellence. They flew the aircraft they were given, against targets they were assigned, with weapons they did not choose, producing effects they could observe but not always reconcile. August 1945. Two B-29s, Enola Gay and Boxcar, would carry atomic weapons against Hiroshima and Nagasaki, missions that would end the war and inaugurate the nuclear age. These aircraft incorporated every technical improvement developed during the B-29 program, including the oversized cooling systems that enabled the long-range precision missions required for atomic weapons delivery. The cooling manifolds that had seemed absurdly large in March 1944 were now understood as essential components of the most consequential weapons platform in human history. Colonel Paul Tibbett selected his aircraft specifically for mechanical reliability. The B-29s chosen for the 509th Composite Group underwent inspection regimens that bordered on obsessive. Every component was tested beyond normal specifications. The cooling systems received particular attention because engine failure during an atomic mission was not merely a tactical problem. It could mean detonating a nuclear weapon in an unintended location or losing the device over the ocean. The engineering margins that had been built into the oversized cooling system now served as safety margins for weapons that could destroy entire cities. The technical requirements were absolute. The aircraft had to reach the target at precise altitude and speed, deliver the weapon accurately, execute the escape maneuver, and survive the shock wave from a weapon whose effects were still being calculated. Engine reliability was not the only factor, but it was fundamental to everything else. When Enola Gay lifted from Tinian in the pre-dawn darkness of August 6, 1945, its Wright R-3350 engines were running with the smooth precision that had become characteristic of the modified cooling system. The flight to Hiroshima covered 2,500 miles in 6 hours. Engine temperatures remained stable throughout. The weapon was released at 31,000 feet with the aircraft operating at optimal performance. The mission executed exactly as planned, enabled by engineering that had transformed a problematic aircraft into a reliable strategic platform. The moral weight of that reliability was almost unbearable. The cooling system that had saved countless American lives by preventing mechanical failures had now enabled a weapon that killed 70,000 people instantly and would ultimately claim more than 200,000 lives. The engineering achievement and the human catastrophe were inseparable. Technology had created possibility. Human decision had created reality. The consequences would echo through generations. The final accounting of the B-29 program reveals numbers that capture both triumph and tragedy. From 1943 through 1945, Boeing, Bell, and Martin produced 3,970 B-29 aircraft. These aircraft flew 31,000 combat sorties, delivered 171,000 tons of bombs, and achieved mechanical reliability rates that exceeded all previous American bomber programs. The oversized cooling system that had seemed wasteful in 1944 proved essential to every aspect of this performance. The loss rate told its own story. The B-29 fleet lost 414 aircraft to enemy action and 147 to operational accidents, but mechanical failures as primary loss factors dropped to below 2%, a rate so low it was almost unprecedented in aviation history. The cooling system had achieved its fundamental purpose. It kept engines running when failure meant death. Yet the strategic impact of this reliability transcended mere survival statistics. The B-29 enabled a strategic bombing campaign that devastated 67 Japanese cities, killed between 300,000 and 900,000 civilians depending on how casualties are calculated, and culminated in the only combat use of nuclear weapons in human history. The engineering that prevented mechanical tragedy enabled strategic catastrophe. This was not the fault of the cooling system or the engineers who designed it. Technology has no moral agency, but the human choices enabled by technical capability carry moral weight that engineering calculations cannot capture. The B-29's reliability meant that commanders could plan missions that would have been impossible with unreliable aircraft. The thermal stability provided by oversized cooling manifolds translated into operational flexibility that allowed precision nuclear strikes and area incendiary bombing with equal mechanical efficiency. In the end, the question was never whether the cooling system worked. It worked magnificently, better than the designers dared hope, exceeding specifications in ways that redefined what strategic bombardment could achieve. The question was what that capability meant in human terms, measured not in thermal transfer coefficients or engine operating hours, but in cities burned, lives destroyed, and a war brought to conclusion through the application of industrial killing power on a scale that previous generations had not imagined possible. The oversized cooling pipe had turned the B-29 into a long-range powerhouse. What humanity did with that power remained a moral reckoning that no amount of engineering excellence could resolve. The B-29 Superfortress would continue in service long after the war ended, flying combat missions in Korea, serving as the platform for early strategic nuclear deterrence, and providing the foundation for the Boeing 377 Stratocruiser that helped inaugurate commercial transoceanic flight. The cooling system innovations proven in combat influenced every subsequent generation of high-performance aircraft, military and civilian. The engineering lessons learned between 1943 and 1945 shaped aviation design for decades, but the human legacy proved more complex than the technical achievement. Veterans of the B-29 campaign carried contradictory memories: pride in technical mastery, horror at destruction witnessed, gratitude for survival, and moral ambivalence about missions that saved American lives while claiming Japanese lives on a staggering scale. Edwin Hartley, the engineer who had questioned the oversized cooling manifolds in March 1944, lived to see the Boeing 747 make its first flight in 1969. The jumbo jet's engines incorporated thermal management principles proven on the B-29. The direct lineage was clear. "We solved a problem," he said in a 1970 interview. "Engine cooling at high altitude under sustained load. It was a legitimate engineering challenge. But engineering exists in context. The cooling system we designed enabled missions I'm still not sure were necessary. Both things are true. The engineering was sound. The uses were complicated." This tension between technical achievement and moral consequence defines much of modern technology. The capability to do something does not resolve the question of whether it should be done. The B-29's oversized cooling pipe represents this paradox in physical form, a component that worked brilliantly to enable operations whose necessity and proportionality remain subjects of historical debate 70 years later. What remains beyond debate is this: a design decision made in early 1944 to oversize a cooling manifold transformed an unreliable experimental aircraft into the most capable strategic bomber of World War II. That transformation saved lives and took lives, advanced aviation and demonstrated destruction, solved technical problems and created moral dilemmas. The cooling pipe did not make these choices. Humans did. But the engineering that seemed excessive in Seattle became essential over Tokyo, proving that sometimes the path to reliability requires building in margins that cautious optimization would eliminate. Sometimes you make the pipe bigger, carry the extra weight, accept the added cost because the margin between success and failure is measured not in efficiency, but in lives. That was the lesson of the B-29's cooling system. It remains relevant every time engineering confronts the gap between what we can build and what we should build with the capabilities our building creates.